Morning and welcome to the lecture series on numerical analysis. So in this lecture we will study about the numerical solution of ordinary differential equations. So to describe various numerical methods for the solution of ordinary differential equation, we consider the general first order differential equation dy by dx equals to function of x comma y with the initial condition y at x0 equals to y naught and illustrate the theory with respect to this equation. There are various numerical methods for the solution of ordinary differential equation, which are mentioned below. Out of them, first four methods we have already covered in the last lectures. So in this lecture, we will study about the Runge-Kutta method. So the Runge-Kutta method are designed to give greater accuracy, and they possess the advantage of requiring only the function values at some selected points on the subintervals. So consider the differential equation dy by dx equals to function of x comma y with initial condition y at x0 equals to y naught. Now if we integrate this differential equation over the first subinterval x0 to x1, then we obtain this relation y1 equals to y0 plus integration from x0 to x1 function of x comma y dx. Now if this integrand function of x comma y is replaced by the average slope at the point x0 and x1 as we did in modified Euler's method, then we obtain this relation y1 equals to y0 plus h upon 2 times slope at x0 plus slope at x1. It means if this integrand f of x comma y is replaced by the average slope at the point x0 and at the point x1, then we obtain this relation, which we have already derived in the modified Euler methods. Now, if we substitute y1 equals to y0 plus h times slope at x0 in the right hand side of this above equation, it means this y1 is replaced by this value, which is obtained by using simple Euler's method. Then we obtain this relation y1 equals to y0 plus h upon 2 times function slope at x0 plus slope at x1 y0 plus h f0. Now here f0 means slope at x0 comma y0. Now if we take this one hf0 equals to k1, it means slope at x0, and k2 is the slope at right hand of the interval. It means slope at x1 x0 is if we take k1, and slope at this point x1 is if we take k2, then we obtain y1 equals to y0 plus 1 upon 2 times k1 plus k2. So this, it means this is our k1 and this is our k2, right? So y1 equals to y0 plus 1 upon 2 times k1 plus k2, which is the second order Runge-Kutta formula. It means this represents that y1 equals to y0 plus weighted average of the slope in the interval x0 to x1, where weights are 1 upon 2 for each point x0 and x1. So in general, in the xn plus 1 interval, we can write second order Runge-Kutta method as yn plus 1 equals to yn plus 1 upon 2 times k1 plus k2, where k1 is the slope at the point xn and k2 is the slope point at the point xn plus 1. Now, analogously, the fourth order Runge-Kutta method is given by this relation. Now, this is our weighted slope with different weights. At the initial and end points, the weights are 1 upon 6, and in the midpoints, the weights are 1 upon 3. Alright, where k1 equals to slope at this point x0, and k2 is the slope at the midpoint of the interval. It means somewhere here, which is x0 plus h upon 2. And k3 is the slope at this point, midpoint again, x0 plus h upon 2. And k4 is the slope at this point, x1. So this is our Runge-Kutta fourth order method. For the detailed derivation, you may go through any numerical methods book. Right? Or in general, in the xn plus 1 interval, this Runge-Kutta fourth order method is given by this relation, where k1 is the slope at the point xn, k2 is the slope at the midpoint of the interval xn and xn plus 1, k3 is the slope at the midpoint of the subinterval, and k4 is the slope at the right hand point of the interval. Now Let us see application of Runge-Kutta method. So given differential equation dy yx equals to x times y minus x, initial value is given at x equals to 2 equals to 3 in the interval 2 to 2.4. Using RK fourth order method with the step size h equals to 0.2, we have to find the solution of this differential equation. So we have given slope of the differential slope of the curve is x times y minus x and h equals to 0.2. So we take x0, it means initial point of the interval. It means we are given h equals to 0.2. So our interval 2 to 2.4 is divided by two sub-intervals. First one is 2 to 2.2 and second one is 2.2 to 2.4. Now first we find the value at this point 2.2 because we know the value at x equals to 2 which is 3. So first we find value of the function y at this point x equals to 2.22 and then we find value of the function y at this point 2.4. So we take x0 equals to 2 and y0 is given already 3. So we obtain from this Runge-Kutta fourth order equation which is given by 3. So k1 is the slope at this point x0. So it means h means 0.2 times function slope at x0. It means x0 means 2 times 3 minus 2 which is 0.4. K2 is the midpoint. It means somewhere here which is 2.1. So 0.2 times 2.1 times 3.2 minus 2.1 equals to 0.4620. Right? Because here, if we replace x is replaced by this x0 plus h upon 2 and y is replaced by y0 plus k1 upon 2 because we know y0 equals to 3 and k1 upon 2 means 0.2. So this is 3.2. So this y0 plus k1 upon 2 it means 3.2. And x means 2.1. If we simplify, then we get 0.4620. Similarly, k3 is given by this one 0.2 times 2.1. Now this one, it means y0 plus k2 upon 2. K2 upon 2, it means 0.2310. Alright, plus this one, it means 3.231 minus 2.1. If we simplify, then we get 0.4750. Similarly, K4 is the slope at the right end of this interval. It means at 2.2. So this is 2.2 times 3.4750 minus 2.2 equals to 0.5610. Now, if we substitute these values in the relation number 4, then we get 3 plus 1 upon 6 times. This is our K1. This is 2 times of K2 plus K3 plus K4. Now, if we simplify, then we get 3.4725. which is correct to 4 decimal places. So this is our value of the function y at the point 2.2. Now to compute the value y at 2.4, we take x0 equals to 2.2. It means we are interested to find the value of y at this point. So therefore we take this point is initial point x0 and we know that the value of the function y at this point 2.2 which is 3.4725. So, and step size is already given, which is 0.2. With these values, equation 3 gives k1 equals to 0.5599, k2 equals to 0.6682, k3 equals to 0.6930, and k4 equals to 0.8474. Now, if we substitute these values in equation number 3, then we obtain y at 2.4, which is 4.1608, which is correct to 4 decimal places. Let us see one more example. dy by dx equals to 1 plus y square with the initial condition y at 0 equals to 0. Find the value of y at 0.2, 0.4 and 0.6. So we take the step size h equals to 0.2 with the initial condition x0, y0 equals to 0. We obtain from the RK fourth order method which is given by equation number 3. K1 equals to h times of function of x0 comma y0. Here, if we put this is our function of x comma y. If we put x0 equals to 0 and y0 equals to 0 in this relation, then we get 1. So this is h times of f0 which is 0.2. Similarly, k2 it means slope at the midpoint of the interval. It means 0 and 0.2 which is 0.1. So if we simplify, then we get K2 equals to 0.202. Similarly, K3 equals to this one and K4 equals to this one. Now, if you substitute these values like K1, K2, K3 and K4 in the RK fourth order method, then we get Y at 0.2, which is 0.2027. This is the value of the function at the point 0.2, which is correct to 4 decimal places. Now to compute the value at the next point 0.4, we take x0 equals to 0.2. It means this point, and y0 equals to corresponding value, which is 0.2027, and h equals to 0.2. And preceding as above, we obtain y at 0.4 equals to 0.4228. And finally, if we take x0 equals to 0.4, it means previous point, and y0 equals to this value 0.4228 and h equals to 0.2. And proceeding as above, we obtain y at 0.6 equals to 0.6841. Right? Now, we consider the initial value problem, y prime equals to 3x plus y upon 2 with the initial condition y0 equals to 1. In this example, we compare the results of Euler's method or modified Euler's method and Runge-Kutta methods. So the following table, which is given in the next slide, the value of y at 0.2 by different method, the exact value is being 1.167222193. Now it is seen that the fourth order RK method gives the accurate value for h equals to 0.05. H means step size. So there are various numerical methods. We have solved this problem by using Euler's method for different step size, modified Euler method and RK method of fourth order. So now if we take h equals to 0.2, then we get by Euler's method 1.10. If we take step size, it means if we divide the range of integration 0 to 0.2 by 2 subintervals, then we get 1.13250. Now if we divide our range of integration 0 to 0.2 into 4 subintervals, then we get 1.14956758. If we use modified Euler method for step size h equals to 0.2, then we get 1.10. If we take step size h equals to 0.1, it means we will divide our range of integration into two subintervals 0, 0.1 and 0.2. Then we get, this is y at 1.2, right? If we take the step size h equals to 0.05, then we get y at 0.2 equals to this 1.162 and so on. Similarly, if we use RK fourth order method, then and if we take the step size h equals to 0.2, then we get y at 0.2 equals to this one. If we take this step size h equals to 0.1, then we get y at 0.2 equals to this one. And if we take step size h equals to 0.05, then we get y at 0.2 equals to 1.1622193, which is exactly same as the exact value of the function at y equals to 0.2. So it means your fourth order RK method gives the more accurate result compared to the earlier methods such as Euler's method, Picard's method, Euler's method, modified Euler's method. So this is very important method for practical use, and it gives more accurate values compared to